Hello scientists, we're going to work on activity 4 in the Concord Consortium High Adventure Science module called What is the Future of Earth's Climate? We're working on sources, sinks, and feedbacks in Earth system models of climate change. So let's go look at carbon cycling in Earth systems. Carbon dioxide is constantly being added to the atmosphere through both geological and biological processes. Things decay, carbon dioxide gets added to the atmosphere. We breathe out, we are adding carbon dioxide to the atmosphere as we breathe. As rocks are weathered, carbon dioxide is released. Living organisms release carbon dioxide through respiration, and when they die, they release carbon dioxide as they decompose. Extra carbon dioxide is released when materials are burned. These are all sources of carbon dioxide. With all this carbon dioxide being added, why isn't the CO2 level in the atmosphere much higher? Well, it turns out carbon dioxide is also being removed from the system. Like water and other substances on Earth, carbon dioxide is recycled. This means that carbon dioxide is neither created nor destroyed, but moves between various reservoirs or storage spaces on Earth. The spaces that can take in carbon dioxide are called sinks. So the ocean can take in carbon dioxide. The carbon dioxide can bond with more oxygen and calcium and create calcium carbonate, which is part of the sediments. This is limestone. Then those sediments can move up through tectonic plate action, can move up and become part of land. They can weather and go back into the atmosphere. The atmosphere can deposit carbon dioxide on land. Rain can absorb carbon dioxide in the air and become carbonic acid. The ocean can absorb carbon dioxide, just like a soda can have bubbles in it. Liquids can absorb carbon dioxide. And that carbon dioxide can also leave the ocean, just like bubbles leave your soda. The flowchart shows the movement of carbon dioxide between Earth's carbon reservoirs. For example, carbon dioxide in the atmosphere can come from the land or the ocean, and also can be stored in the ocean or the land. Follow the arrows in the flowchart to see how carbon dioxide moves between different reservoirs. Which statement is true about the carbon dioxide cycles? Reservoirs add more carbon dioxide to the environment than they remove. Carbon dioxide travels through the environment in a single direction. Carbon dioxide is constantly moving throughout the environment. When carbon dioxide enters a reservoir, it no longer cycles. Well, to me, when I look at this model, it looks like carbon dioxide's always moving. It doesn't ever stall out anywhere, because if we see these arrows, they're going out and in and out, and in and out. So it's not ever stalling out anywhere. It's always cycling. Even though it might spend, millions of years as part of sediments, it's still going to get recycled. Is there a reservoir that serves only to take in carbon dioxide? So if we look at this model here, is there a place where an arrow is only going in? It looks like that might be true for sediments. It's coming in here, but we can see the arrows also going out. So reservoirs or sinks are also sources. Of CO2, which is just short for carbon dioxide. All right, let's keep moving here. We're on page 2. Carbon dioxide is soluble in the ocean. If you've ever had a soda or carbonated water, you know about solubility of carbon dioxide in water. The ocean has many substances dissolved in it, including salt. If you try to dissolve salt in a glass of water, you'll find that the more salt dissolves in the water, more salt will dissolve when the water is warmer. The solubility of the salt in water how easy it is to dissolve in water is affected by temperature. So generally, if you want to dissolve sugar or salt in water, you make the water warmer. If you've ever made candy, you boil the water, you add the sugar, and you can get a lot more sugar to dissolve in water if it's very hot than if it's not. The solubility of gases is also affected by temperature. How does the solubility of a gas change with temperature? The picture shows the model you use to answer this question. It shows the interactions between Earth, land, ocean, and atmosphere. Well, let's look at the solubility of gases as they are affected by temperature. So I heated up some hot water in the microwave, and this water is carbonated. And you can see that the carbonation is leaving this hot water pretty quickly. This is carbonated water that I didn't heat. And there's some bubbles moving in there, but not as fast as the water I put in the microwave. That carbon dioxide is just running out of that water like crazy. Hot water doesn't hold gas very well. And you know this if you've ever had a soda. If you put ice in your soda, it's going to stay fizzy longer. All I did is take a bottle of water and put it in a carbonator. You may know someone with a soda stream. And add some carbon dioxide to that water. And then I added a little dye to the water. And heated the red water, but didn't heat the blue water. And you can see the difference in the carbon dioxide coming out of those two glasses. Just to note the difference in temperature, the cold one is 12.5 degrees Celsius, and the hot one is 30 degrees Celsius. So there's quite a bit difference in temperature. And you can see that hot water doesn't hold carbon dioxide as well as cold water. The carbon dioxide stays dissolved in the cold water longer. So now that we know about how water holds carbon dioxide, which you already probably knew because you like ice in your soda, we can think about using the picture of the model to make a prediction about the effect that temperature will have on the ability of the CO2 to dissolve in the ocean. Will the higher temperatures increase or decrease CO2 solubility? Well, here's CO2 in the atmosphere. Here's CO2 in the ocean. Here, the CO2 in the atmosphere is going way up, but the CO2 in the ocean isn't going up. The temperature is going up. You can see the air temperature here on the red line, and the ocean temperature is going up. So the ocean is getting hotter, and when the ocean gets hotter, that carbon dioxide leaves the ocean. Hotter liquids do not dissolve gases very well. That's why we put ice in our soda, so it stays cold and it stays fizzy. If you leave your soda out on the counter on a hot day, it gets hot, it goes flat very quickly, and it's not as good as a soda that's fizzy. So, carbon dioxide is a gas, and it will not dissolve well in the ocean when the ocean is warmer, because gases do not dissolve well in warmer liquids. If we think about the molecules in a warmer liquid, they're moving faster, and it's harder for the gases to stay attached to molecules that are moving faster. So these faster molecules don't dissolve gases as well. They do break apart solids well, like salt or sugar, but they don't hang on to gases well. So now let's figure out how the ocean temperature might change. using the temperature slider below the model to increase and decrease the temperature of the ocean. So we have a slider here. We can be the master of the universe and change the temperature with the slider. The temperature of the ocean is shown with the blue line. So let's get this model going. Notice that the ocean temperature lags behind the air temperature. So let's turn up the temperature here. So we're turning up the air temperature. You can see that the blue line takes a little bit longer to come up than the red line. That's because air heats much more quickly than water. If you've ever gone swimming in May, right after a lake, the ice gets off the lake, you know the lake is still pretty cold. It takes a while for our lakes to warm up in the summer because water warms much more slowly than air. It has a high heat capacity. So as we increase the air temperature, the CO2 in the atmosphere is going up, but the CO2 in the ocean doesn't increase. What happens is that as the ocean temperature heats up, the ocean is actually losing carbon dioxide like the hot carbonated water, and that carbon dioxide goes into the air. Which graph shows the temperature of the ocean? Let's look. So here's temperature changes. Here's air temperature and ocean temperature. So it's the upper graph here that shows temperature changes. Which color line represents the amount of CO2 in the atmosphere? So let's look at the key. You can press key here if you don't have this key. CO2 in the atmosphere is a green line. CO2 in the ocean is a blue line. So CO2 in the atmosphere is right here. And it keeps going up and up and up. How does the water temperature affect the amount of carbon dioxide that can dissolve in the ocean? Well, we know hot carbonated water or hot soda doesn't hang on to its fizz very long. Doesn't hang on, gas does not dissolve in hot water well. So as we heat the ocean up, the carbon dioxide is going to fizz out into the atmosphere, and the atmosphere is going to have more carbon dioxide. The ocean will have less carbon dioxide and the atmosphere will have more. Which statement best describes the relationship between temperature and solubility of carbon dioxide in the ocean? Like hot soda, the hot ocean is going to have less carbon dioxide dissolved in it. The carbon dioxide is going to bubble out of the ocean. It's not going to be dissolved anymore. And it's going to go into the atmosphere. Of course, in the real world, we can't just magically change the temperature of the Earth with a slider. Which choice best describes the relationship between the atmospheric CO2 levels and the absorption by the ocean? When the atmospheric CO2 levels become higher, the temperature becomes higher. The air temperature becomes higher. Because the blanket around the Earth, the atmosphere, is thicker and holds more heat. It re-radiates more of that, the carbon dioxide re-radiates more of that infrared heat back to the Earth. So as we add carbon dioxide, we get warmer. As the air temperature comes up, the ocean temperature comes up too, and we can see that if we raise it a little bit. It lags a little bit behind, but we can see that the air temperature rises, the ocean temperature eventually rises as well. The ocean gets saturated with carbon dioxide, maybe. The hotter water does not dissolve as much CO2, that's carbon dioxide gas. Because gases are less soluble at higher temperatures. This is also true for oxygen. Fish need oxygen in water, so cold water is actually good for fish because cold water dissolves more oxygen than hot water. So fish, especially in the Midwest, like cooler water. When we start to heat up their water, especially some species like trout tend to die because they don't have enough oxygen. How certain are your claim based on your explanation? Well, I'm pretty certain about this one. You can pick your own one. The reason I'm certain is the chemistry of gas solubility in warmer liquids is solid science. We pretty much, you can go to any lab and you can test this, like how well a gas is going to dissolve in cold or hot water. We can see that at warmer temperatures in the model that there is more CO2 in the air, but not much more in the ocean. As the ocean warms, there's actually less CO2 in it because it reaches saturation and it can't dissolve any more CO2. So Hasbot says, my answers are all right. Maybe you want to write a better answer, see if you can get a 6. It's giving me some feedback here. Can you provide specific evidence from the model about how atmospheric CO2 affects temperature? So you can go back to the model, look for this specific evidence, and add it to get a 6. You use scientific evidence or knowledge. That's awesome. But now I need to think about potential weaknesses of my argument. Are there limitations on what you can learn from our ocean model? What are they? Well, I would say this model is a little bit simplistic because it doesn't have any other greenhouse gases in it. It doesn't have water vapor in it. Any model that's simpler and doesn't have all the pieces is not as good at predicting. So the more factors, the more variables, the more things you include in your model, and the more you test your model, the better it is going to be at making predictions. And we don't have all the information in this model. We don't have all the greenhouse gases. We don't have ice caps. We don't have clouds. We don't have water vapor. There's a lot of things we're missing. So that's a limitation of our model that we could add to our explanation in question 12. So now we have to think about water vapor. We're making our model more complex, and if we make a model more complex, that can make it more accurate. Not always. In the previous model, you saw that carbon dioxide traps infrared radiation in the Earth's atmosphere, and the temperature increases with increasing carbon dioxide concentration. So the more carbon dioxide there is in the air, the more opportunity that infrared radiation has to heat up the carbon dioxide and be re-radiated towards Earth, or the blanket gets thicker. What's missing from the model? Well, in the last model, you learned that oceans play a role as a reservoir for carbon dioxide. But oceans play more than one role. In this model, you'll explain the relationship between temperature and water vapor levels. Experiment with the temperature slider below in the model. So let's play with this a little bit and see. Let's get our model going. So the blue dots, we're going to guess, are water vapor. The green dots have always been carbon dioxide. And so now carbon dioxide and water are both acting in the atmosphere to absorb infrared radiation and bounce it back. So let's raise the temperature here and see what happens. If you've ever made noodles or taken a steamy shower, you might have noticed that when you heat water up, more of the water evaporates into the air. If you're in the shower, it steams up your mirror. That water in the air condenses on your mirror. If you're walking around out in the summer and it's really humid, it might be hard to breathe. You might sweat more easily because your sweat doesn't cool your body in the same way when there's humidity in the air. We know when it's hotter, we either get the water hotter or the air hotter or both, there's more water vapor in the air. So as we raise the temperature here, we can see that the water vapor, this black line here, is going up. The CO2 is going up, and as the CO2 makes the air hotter, the air heats the ocean water, and as the ocean water gets hotter, just like the noodle water on your stove, if you're making mac and cheese or maybe you're making rice, as that water gets hotter, more of that water goes into the air. You see more water vapor above your pot of water. What color line represents the water vapor in the atmosphere? Well, let's look at the key here. It looks like black represents the water vapor. Let's check our answer. Ooh, we got it right. How is infrared radiation represented in the model? So all over the model, we've seen infrared radiation as the purple arrow. The yellow arrows are sunlight. They hit the water, and the water becomes a little bit hotter as it absorbs the solar energy, and that heat energy is re-radiated as purple arrows. Those purple arrows can hit the carbon dioxide, warm up the carbon dioxide, and then that heat is re-radiated back to the earth. The same can happen with water vapor. If we put water vapor into the atmosphere, that infrared radiation can also hit the water vapor. The water vapor can heat up, and eventually that infrared radiation will be re-radiated towards Earth. Infrared radiation, so is purple arrows. How does the infrared radiation interact with a greenhouse gas? Well, we know that the infrared radiation hits the greenhouse gas. It makes the greenhouse gas vibrate more, which represents a hotter molecule. And then eventually when that molecule cools down, that infrared radiation will be re-radiated or released back into the atmosphere. And so it basically goes in and comes back out towards the Earth. Sometimes it doesn't always go towards the Earth, sometimes it'll go sideways, maybe it'll go into space, but often it comes back towards Earth. Greenhouse gases absorb radiation, they heat up a little bit, they vibrate faster, which is the definition of temperature. Molecules vibrate faster, have more energy when they're hot, and then they let go of that energy, they cool down and re-radiate that energy towards Earth, maybe sideways, maybe into the atmosphere, but mostly back towards the surface of planet Earth. What's the relationship between water vapor and temperature? Well, we know that water vapor is a greenhouse gas. So like other greenhouse gases, it can absorb infrared radiation and re-emit it towards Earth. Water vapor is a greenhouse gas. It can absorb infrared radiation and re-emit it towards Earth, heating Earth. So like other greenhouse gases, water vapor can keep the planet warmer. Water vapor is a greenhouse gas. What do you think the temperature will happen to the temperature when you increase the amount of water vapor? See what you think and then try to explain your answer. I gave you some pieces to think about up here, and we talked about what happens when water vapor absorbs infrared radiation. It vibrates faster, and when molecules are vibrating faster, that represents a higher temperature. Temperature is the average energy of the molecules. The molecules cool down, they vibrate slowly, and they re-emit that energy, which often goes back towards Earth and heats Earth. How certain are we about our claim? Well, I'm pretty certain. I know how steamy it feels in the shower when there's a lot of water vapor. I know how steamy it feels in the summer when we have a very humid day. I know that cloudy nights in the winter are warmer than clear nights. So I'm pretty sure water vapor does a pretty good job of holding in Earth's heat. There are some limitations to this model. We're missing some of the greenhouse gases. We don't have any clouds. We don't have ice caps. We don't have deforestation. There are a lot of pieces to this model. It's pretty simple. It is a good way to learn, but it might not be a good way to make predictions because we need something with more complexity. So the model certainly has limitations, which is going to limit our certainty. We'll continue activity 4 in the next video. Thanks for watching. This is Dr. B signing off.